I'd like to remind you that for more Microsoft webcasts, you can go to microsoft.com/webcast. Thanks again for joining us for today's presentation, MSD and Webcast, C# Soup to Nuts, Part 4, C# Program Structure. Now it's my pleasure to introduce today's presenter, Bill Steele, Senior Developer Evangelist. Bill, you now have the floor.
Thank you, Sydney, and welcome everybody to this fourth part of this multi-part series on developing C# applications, C# Soup to Nuts. Today we're going to talk about the infrastructure of a program written in C#. So what we're going to actually cover is, in order for us to actually understand how our software is actually running inside of C#, we actually need to have a little understanding of how it's running underneath the covers. So that's what we're doing today. We're going to take a look at the actual .NET framework itself, look at the architecture of the application, the architecture of the actual framework, and then we'll dig a little bit deeper into that, take a look at the common language runtime itself and some of the benefits that it provides us. And then we'll wrap up the day with a complete overview of what an application in C# actually looks like, including how it interacts with the framework and how it interacts with other types of applications that are available to us as a developer on the .NET framework. So let's start off by taking a look at a real simple overview of the .NET framework. I actually was around at the beginning of the .NET framework. It was kind of neat to see it kind of evolve. The project that was called COOL, C-O-O-L, the C object-oriented language, was the C# language, and the .NET framework, interestingly, had some code names. One of them that most people refer to it as is the Visual Basic Runtime. That made it pretty non-interesting to a lot of developers out there, so they didn't ask too many questions about that because we had always had a Visual Basic Runtime, so that was kind of a good way to hide it under the covers. Anyway, when we released that at the I believe it was the 1999 PDC, we had a lot of interest from people out there, and we decided to try to get it as a standard. So we submitted it to the ECMA body as well as the ISO standards body, and they both subsequently ratified it as a standard in 2001 and 2003. Now, what they ratified as a standard is actually what we call the CLI, the Common Language Infrastructure, as well as the C# language itself. So there was some. This does make it available so that others can implement that, and we've actually seen the C# language and the CLI implemented on other platforms due to this release. Now, we actually had set about with a bunch of design goals in mind when we designed the .NET framework itself. And one of those was that we had the ability to, allow developers to develop in any language that they wanted to, as long as it was a managed code-based language. And with that in mind, we set about defining an infrastructure that allowed any language to really exist on this platform, as long as it adhered to a few certain things. For example, it had the ability to compile down to the intermediate language, and that there was no dependencies outside of what we included in the box, if you will. However, that allowed us to really expand the development platform way beyond anything that we'd seen in the past. As a matter of fact, the Common Language Infrastructure and the .NET framework itself, having the ability to run multiple languages, actually was the first time where a broad adoption of a multi-language platform was available. Now, the CLI actually includes some very basic things. For example, it allows any application running under it to be free from having to deal with their own memory management. And this is actually a really key feature of the .NET framework, in that it allows developers to focus on developing the code that's important to the business process at hand without having to do the mundane stuff of allocating and deallocating and reorganizing memory. In addition to that, it brings a whole bunch of other things to the table, things like a shared exception handling model, so that, no matter where the code is at, no matter how far deep down you are into the stacks, the calls and everything, when an exception occurs, it's a common type of an exception system that can bubble all the way up to the very root operating system, so that the .NET framework itself, for example, can handle it. And that actually makes it really handy so that you have, a common exception handling system, regardless of what language and what platform you're running on. Some of the other benefits of the CLI, though, excuse me, revolve around the security model. And the fact that we are running managed code. Managed code means that we have a runtime that is actually handling the execution of our code. And it's also doing a whole bunch of other things for us. It's handling the memory, for example. But it's also ensuring that the data types that we're passing back and forth between function calls are valid data types. And it's also responsible for doing things like ensuring that the call is allowed to be actually called by the caller. So there'll be additional data added to the assembly that we saw last week, for example, with the metadata, that describes what kind of security context is required for the code to run. And if there are credentials required, where do they come from and how do they apply to this bit of code? So there's some really interesting things that the CLI does beyond just the execution of our code. Now, these actually lead to some really neat things. For example, they allow us to develop an application, and because it compiles down to this common language mechanism that we use called the intermediate language, it allows any language, any higher level language to be used to develop applications. And not only does it allow any higher level language to be used, but it also allows the mix of any higher level languages. So, for example, it's quite often to see Visual Basic and C# application developers working on the same team on the same project. Because both of those teams, though they might use a different language construct itself, but they develop their applications on the CLI, they compile down to the same intermediate language which can be processed by the same runtime. So that helps us attain a much better application platform, much easier to develop for, much more robust, and it allows business decision makers who are needing applications to develop to pick the right tool for the right job, as well as the right developer for the right job, so you can fully utilize the developer's skills at what they're good at. Now, looking at the .NET framework in overall, we can break it down into a very few basic components. The first one and the most important one is what we call the CLR, the Common Language Runtime. The Common Language Runtime is actually the execution engine that handles all of the aspects of any application that's running in the .NET framework. That CLR is responsible for not only executing your application, but it does a bunch of other magic things. For example, it actually compiles your application. It takes that intermediate language that the Visual Basic or the C# compilers actually produce, and it converts it into the raw native machine language that the computer that it's running on understands. Not only does it do that, though, it also allows it to take that compiled information and actually store that in a cache for later use. By having it stored in that cache, you can refer to it without having to recompile it, and basically get the benefit of having a pre-compiled application with the minor cost of having the pre-compiler actually run right before you execute the code on the first time. In addition to dealing with the compilation and execution of it, the CLR also is responsible for interfacing your code that you write with a set of code that's contained within the system called the base class libraries. The base class libraries are probably one of the most important aspects of the .NET framework because they contain all of the routines, the normal functions and things that you would normally use in an application that are available to you as a library of code. But they do it in such a way that they are shared across any application that wants to use it. So, for example, a very simple object like a string, there's a definition of the string in the base class library called system.string. And system.string is the same string that you would use whether you're in Visual Basic or C# or F# or any code that's running on the .NET framework. And that's really, really an important aspect of the .NET framework is this base class library that you use as a common type across all of the applications. Now, in addition to the CLR and the base class library, you're going to find other things in the .NET framework, and those two in particular are going to be the generic assemblies that you might have Maybe they're pre-compiled libraries, or maybe they're assemblies that you've run, and it's just loaded into memory. Those assemblies are basically, in-memory libraries of code that you can, functions that you can just simply call into. And then outside of that, you have your application itself, and your application will actually get compiled into its own assembly. But notice how I have in this picture, I have your application kind of outside the CLR, and I have some assemblies inside the CLR. The reason I did that is because you can have multiple assemblies available to multiple applications, where generally your application will be the only one running for your particular purpose. There might be other applications that are also running that are, next to, or running in, because we're in a multitasking environment, running alongside your applications that also happen to use the .NET framework. However, in order to make things efficient, we don't compile and build separate sets of libraries from the base class library for each one of the applications it's running. Instead, we actually create one instance in memory and store that in what we call the global assembly cache, so that all instances of, or all running applications can use that one instance of that library, which makes it much more efficient. So, for example, that system.string object exists somewhere, and the definition of that object and all the functionality related to that is stored inside of the base class library, but that gets compiled into an assembly that we can then use in our code later on. So how does this all fit together? Well, it actually fits together really simply. We take our C# applications, we take any resources and any libraries that we're referencing, and we consider that to be our source code. We then take that, or our C# project. We then take that C# project, package it all up, and pass that off to our C# compiler. Now, this says the C# 2.0 compiler, but it can be any version. This happens to be an older slide deck. We have the C# 1.0 compiler, the 2.0, and now we have there's the 3.0, 3.5, and 4.0 compilers. But they all roughly do the same thing. They take your code, they compile it into intermediate language, they use references and resources to add additional metadata to the application, and that all gets packaged up as the managed assembly. Now, that assembly can either be an executable file or a DLL library, but in either case, it gets packaged up as an assembly with the intermediate language in it. When you execute that code then gets passed off to the .NET framework itself, where the runtime will open up that code. It will inspect the metadata within that assembly, run some security checks. If it finds that everything is good on the security checks, it will then go through and fire off the just-in-time compiler on the first time this code is run. The just-in-time compiler will convert the intermediate language code into the true machine language for that machine that it's running on at that point in time. And that's actually one of the beauties of the just-in-time compiler, is that it can do this very, very rapidly and efficiently, and it, interestingly enough, only does it for the code that you're actually asking to be run. There are ways that you can ask it to compile everything. However, in most cases, that's not necessary. Once that is compiled, that is actually stored inside of the execution cache on the machine, and then the code is executed. In addition to that, it goes through and it actually sets up any references that you have to any of the base class libraries, and if they haven't been compiled yet, it will also pre-compile them or JIT compile them. And then lastly, it will go ahead and allocate and execute your memory mechanism, whatever it is you need to store your memory, and it'll turn on what we call the garbage collector, which I'll talk about in a little bit. Once all of that magic is done, then we actually pass the output of that, which is native compiled executable code, off to the operating system for it to execute. So that hopefully gives you a quick overview of maybe a 30,000-foot view of how the .NET framework actually works. And now we'll go ahead and start digging in a little bit deeper. So one of the benefits of the CLR itself is a thing that we call the common type system. The common type system is a mechanism that allows any developer to know and understand the types of variables or the types of objects that any other developer might use. In the old days when we were developing applications, one of the problems that we had was that you would have one type of application that would use a string and another type of application that would use a string, yet those two strings were totally incompatible. So, for example, Visual Basic 6 and Visual Basic 1, for that matter, used a string format called the VB string. In that VB string, you would actually have a length defined ahead of it, and it would tell you how many of the preceding bytes represented that string. So if I had the word Bill as a string, it would start off with, in memory, it would actually have the value 4, and then the 4 letters indicating Bill to tell you how long it was, and then the 4 letters that actually had the value of it. So you had 5 bytes representing how long the string was. Now, in C or C++, we actually had a different mechanism. We had what we call a null-terminated string. In a null-terminated string, there was no indicator of how long the string was. Instead, we actually would have the 4 bytes indicating the string, B-I-L-L, and then the 5th byte indicating the end of the string, which was a 0, so a null. And we would call those null-terminated strings. Now, different systems use different formats for dealing with that string. And if you were a VB developer wanting to integrate with some C++ code, for example, you would actually have to make sure that you created the correct instance of the string and passed it off to the C++ code, or the C++ developer would have to have another method set up specifically to take the VB-style calling or string convention. And that was a real headache, and that caused a lot of problems. So with a common type system, we've kind of eliminated that problem. The way the common type system works is we, in our code, don't define what a string is. Instead, we rely on the framework to define what a string is. And in fact, in the system namespace, there is an object called system.string. And anybody that's a developer, anybody developing an application that wants to use a string should use the system.string class for its definition of a string. And if they do that, then we can not worry about the language barriers between, data types. We can simply start, create a string, pass it off to the other developers, language code, whatever, and they can automatically say, okay, this is a string, I already know what it is, and I don't have to do any conversions on it. That allows us to not only have this nice human readable style system, but it also allows the .NET runtime to understand, hey, this method call is receiving this type of string, and if I don't see that type of string coming in, then I'm not going to allow the call to occur, which actually protects the system. That's actually one of those things that the Common Language Specification helps us define. That CLS in the Common Language Infrastructure itself has this mechanism that says, okay, I know what a string looks like, I know what this method call looks like, I can match these two up and say, yes, this is a good function call that's not going to hurt anything. So that's actually a pretty important aspect of it. With the Common Language, Common Intermediate Language as a requirement of the Common Language Infrastructure, every language that you use, whether it's VB, C#, F#, whatever it happens to be, COBOL, they all have to compile down to the Common Intermediate Language, or the Intermediate Language IL. In those cases, when you build a language, the specification actually defines the types of objects that you use and how they get constructed and how the intermediate language has to look when you're done with it. Those rules, which were defined in those standards, by the way, those rules that dictate what a language looks like help us in building an application that is, optimized for this runtime environment where we can have multiple developers working in, the languages that they know the best, all working on the same project. And in fact, not even just working on the same project, they can actually be working on in some cases, the same class, which is an interesting concept that we'll look at in the future. One other aspect of the .NET CLR itself is this concept of a just-in-time compiler. Now, I talked about this a little bit ago, but what a just-in-time compiler actually is it is a compiler just like the VBC or the CSC compilers that we used earlier to build a C# app or a Visual Basic app. That's the same kind of concept, except that the just-in-time compiler only knows how to compile intermediate language down into the native machine language that the computer is running on at that point. So you might find that a just-in-time compiler, though you can't actually do anything with it yourself, can be tuned and optimized to suit the specific tasks of what the developer wanted. So there's some really cool, interesting things that are going on in there. Now, the just-in-time compiler is only triggered if the .NET Framework has seen that the code that you're about to execute has not been compiled previously. If it has been compiled previously, what will happen is the .NET Framework will actually have it already stored in a execution cache somewhere in memory. And instead of it having to recompile it, it'll simply jump to that spot in memory and execute that code that's already been precompiled. So this gives us this concept of this virtual execution system where I can actually have an application compiled and optimized on the first run, and then any subsequent runs, any code that's reused can simply be executed right from that point, regardless of what app is actually making the calls into those functions. So that helps us virtualize our code execution model that way. So let's go ahead and pop out to a demo real quick and take a look at the benefits of the common type system and how we can actually use it in some really simple code here. Now, when I move to the next slide, it's going to take us out to my view sharing demo. My computer is set up to 1024 by 768, so if your resolution is that or higher, you can press the F5 key on your keyboard to get a full screen experience. And when we're done with the demo, you can press the F5 key again and return you back to normal. So let's pop out to my desktop, and what I'm going to do is I'm simply going to launch C#, and I'm going to launch an instance of VB.NET. Now, we're going to focus on C# today, and in order to do that, what I've done is I've built a little class library in Visual Basic that does something very simple. It has a simple class in it called class 1 that exposes two methods. Those two methods are getString and getNumber, and each one of them returns a string. But they take parameters. The first one, the getString, actually takes a string as a parameter, and the getNumber actually takes an integer, 32-bit integer in this case, as a number. And they both return a string concatenating the value you pass in with the your name is or your number is text in front of it. So this is a very, very simple Visual Basic class. And what I'm going to do is simply build this class. So I have a late compiled version of it. And now what I'm going to do is I'm going to create a new C# project. We'll just build a simple little console application. And our console application, what we need to do is, what I want to do is I want to call into this Visual Basic library. So I'm going to add a reference to that Visual Basic library, and we're just going to go browse out to that. Now that's class library 2. So we'll go out to class library 2, go down into the code. It's actually in release code. This is called class library 2. Now, class library 2 contains the class in it called class 1, so we'll go ahead and create an instance of that and run that. So what I'll do is, the first thing I'm going to do is I'm going to say using class library 1. Actually, it should be class library 2. There we go. That's interesting. Maybe my namespace is wrong. It is. My namespace is wrong. Look at that. So the root namespace happens to be class library 1, even though the assembly is called class library 2. So that was let's go back to this. Make that sure that's a 1. Okay, so it's not complaining now. And notice how the namespace is different from the actual executable. That's something to be wary of later on. Okay, let's create an instance of this. So we're going to create our class library, which is called class 1. We'll call this C equals new class 1. New class 1. Okay. So I've created a new instance of this class library called C. Now remember, if I didn't use this using namespace up here, I would have had to fully qualify this out by typing in class library 1.class1. So without the namespace, it would have been the fully qualified version of it. So X equals new. So you can see just by using this using statement, I've actually eliminated quite a bit of typing here. Okay, now that I have that, I can go ahead and start making some of those calls. And what I'm just simply going to do is do a console.writeLine. And we're going to use our C object that we just created, and we're going to call the getString method. Remember, the getString method in Visual Basic actually took a value called your name. So we'll say Bill. and console.readKey. Okay, so what I have here is a, get my spacing right, there we go, Control-KD. I have a single line I'm passing in the value Bill, and it's passing it into this method called getString. GetString will then take that string, return a new string called yournameis with whatever value I pass in concatenated to it. So let's go ahead and run this. And there you can see the result is yournameis Bill. So it's concatenated that and returned that just fine. We can also do this with the second number. So here I'm passing in a number, 7718. We'll go ahead and execute that, and you can see I get your number is 7718. So what you're seeing here is this beauty of this type system that allows us to share the types of data, passing it back and forth between two different languages. Even though we're using it in this manner, the system has no problem understanding that the value that we're getting in is a number and the value that we're returning is a string, and it has no problem with me passing in these raw values as well. So it knows that this is the correctly formatted string called Bill. It's not null terminated or it's not preceded with length or anything like that. It's just a string because it is based off of this system.string object namespace. So if I take a look at this guy and go to the definition, actually that's the wrong version of Visual Studio, but the higher end versions of Visual Studio, this is actually the system.string namespace. Oh, there it is. So it comes up. We have our system.string defined here. It's a member of the system namespace. So this actually lets us see, the types of strings and how they're actually formatted. Now notice in the .NET framework that this is actually a series of Unicode characters as opposed to single bytes. But again, that makes it's totally irrelevant to us how we do this within our code. Now, in our next demo, we're actually going to take a look at this in a little bit deeper detail. But before we do that, let's talk about the actual C# language features itself. Now, we just saw one of the aspects of it kind of in a bug just a second ago with the namespaces. In our case, a namespace is a friendly name that we give our class library to help us isolate and filter out or filter down to the specific functions that we want. Now, in my case, I had the namespace 1 as opposed to the actual project name. A lot of times they'll match, or it could be whatever you want. I mean, it really makes no difference, but you just want to be careful that you're getting the right namespace. Namespaces help us organize our code. In C#, there is no concept of a global variable. In other words, when I build a bit of code, there isn't a way for me to say, I want everybody in the world to be able to have access to this. Technically, there is a way to do that, but in reality, it's not what you want to do. The reason we don't do that actually ties into the next one. Is all functions must be a part of a class. Every time you build a method, it has to be contained within some form of a class. The reason we have both of these requirements is all around security. If I'm built as a part of a class, then I can be managed by the framework that knows how to manage that class. But if I'm built as a global object or something that's not a part of a class, you start running into problems where the code might not be known to the system. So, for example, malicious hackers a lot of times will start writing code. They'll do what's called a buffer overrun, and instead of actually executing your normal code like you think you are, they've actually overfilled the buffer and started writing other code in its place. And when your program jumps into that line of code or that point in code where it starts executing, it starts executing the malicious code instead of the good code. With a managed system, because the functions are a part of a class, that is a requirement, only the entry point of a class can actually be the start of execution. In addition to that, that can be monitored by the managed runtime, and the runtime can actually take a look at the data, can take a look at the method signatures, ensure that they haven't been changed or altered, and if they have, it can simply stop executing. So it protects the system by having this type of functionality built into it. Now, I talked about this a while back, but every object within the .NET framework is actually derived from system.object, including even the simplest types. So, for example, a byte. Even though a byte is a single character, a single 8 bits or whatever of memory, it is actually represented in the .NET framework as a complex system.object-based object. So in other words, I can look at a byte and ask it its name. I can look at a byte and ask it its type. Those are things that generally other systems wouldn't allow you to do because they would declare that object as a simple type. It doesn't need to have those aspects to it. But in the .NET framework, because of our security model and because of the way we organize everything, it's easier to think of everything as a system.object-based object, which it is. One other aspect of C# is the fact that we do not have to, when we're building our applications, declare and allocate memory and then deallocate it when we're done. This was one of the pain points of the past development models. In unmanaged code, you would have to declare an object in memory and allocate that block in memory and hopefully ensure that nothing else would overwrite that bit of memory. Because the .NET framework is managed, though, we do have the ability, though, to take a look at your code, determine what kind of objects that you need, pre-allocate those for you, monitor your usage while you're using them, and when you're done using them, go ahead and automatically free up that memory and return it back to the resource pool so that the rest of the application can use it. And we do this through a mechanism called the garbage collector. The garbage collector basically looks at the memory that you have, determines what you're no longer needing, and when it sees that you're no longer needing it, it goes ahead and releases that memory and compacts everything else back up into the smallest amount of space available. This garbage collection routine is something that you do not, as a developer, generally have to worry about. It just happens. You don't have to write any special code or do anything exceptional to make it work. Now, there are ways that you can optimize that. We do talk about that later on in the series. But most generally, you don't have to worry about it. It just happens automatically for you. In C++ or in C in the old days, you would have to do what we call a malloc, a memory allocate. And in those cases, you would have to, check to see that it created the amount of memory that, allocated the amount of memory that you needed for an object. And when you were done with it, you had to ensure that you were done by, adding a reference or releasing a reference or deallocating the memory, whatever it happened to be. This was all a manual process. And with a framework like the .NET framework, you don't have to worry about that anymore. One other aspect of C# is this concept of type safety. Type safety goes back to that one of those things where I talked about the runtime being able to check all objects, check all method calls and signatures. Because it is managed and because nothing can be free-floating, C# can actually take a look at the types of objects that we have and determine that a method that is receiving that object is actually the appropriate type of method to get it. So, for example, when I make a call from one method to another in another class, I might pass a string object in with it. But if the other method signature says, hey, I only take integers, then passing a string would be invalid to it. And we would have to do something to prevent that. So what the C# compiler does is it will actually stop and say, hey, wait a minute, you can't pass the string, it only accepts integers. And it won't let you make that call. And if during the runtime it detects this, it will actually throw an exception as opposed to allowing the call to execute. And this is one of the ways that we make the applications much safer. If we start seeing data that doesn't conform to the signature that the data is, that the method is supposed to accept, then the .NET framework actually will not allow that call to occur, which prevents things like the buffer overruns and memory corruption issues that other systems in the past had. So the last three objects here are things that we're going to be talking about in the future. They're a little bit more complicated than what we need to deal with today, but just it's here for reference here, and when we get to those, we'll point them out. So let's talk about or take a look at variables, functions, and scope, and see how that type safety system helps us, and also see how the lifetime of an object can be handled by the system for us automatically. So let's go ahead and back over to our demo machine here. So our code, remember we had the string and the number methods, and we passed in a string and we passed in a number. Now what I'm going to do is I'm going to go ahead and declare those objects. Instead of using the hard-coded values, I'm going to take this and put them into local variables. So the first one I'm going to do is I'm going to create a string called S, and we'll make it equal to Bill. And then we're going to create an integer called I, and we'll make that equal to 7718. So now I've created this string and this integer. I've assigned them values, and now I'm going to go ahead and use them. So instead of passing in this value Bill, I'm just going to pass in the string S, and the same thing with the number. We're just going to pass in the value I. So I have this parameter now. Instead of being hard-coded, I'm passing in this local variable, and when I execute it, I should get the exact same result, and you can see I do. Now, what has happened here is that we've taken this local variable, and we've created a spot in memory in the either on the stack or in the heap. There's two different types of memory, but in either case, we've created a spot in memory to store this value. And then when I make this method call, I actually pass in the location of this. I say, okay, string, here I want you to use this spot in memory called S that represents my string. That gets passed over to Visual Basic, and the .NET Framework then examines the type of value being passed in here and says, okay, let's make sure the type of data that you're passing is valid and consistent with what this method is. As a matter of fact, if we go back over to our code and we reverse this, let's put the I here and the S down here, you'll notice right away that I get squiggly lines within the Visual Studio environment here. The Visual Studio environment says, hey, wait a minute, I see that you're passing in a string, or you're expecting a string to be passed in here, but you're not passing in a string. In fact, you're passing in an integer. And likewise with your get number, I see you're expecting me to accept an integer, but you're passing in a string. And this can be problematic. The nice thing about it is because we have this type A system, it recognizes this right away and says, okay, let's go ahead and flag the user and let them know that this is a problem. And if I try to compile this, you would see I also get the exact same error. So argument cannot convert from int to a string and cannot convert from string to an int. It turns out there's some magical things that you can do here. An integer, for example, has the ability to convert itself to a string, and a string, you can also take an integer and convert it, a string and convert it to an integer. However, this is not a valid string to do that with. So let's do that, reverse that back out so our code still works. And let's look at one other aspect of this, and that's what we're going to talk about, the scope of an object. The scope of an object is basically the lifetime of that object. How long does it live from the time I create it to the time I'm done with it? In this case, you can see I've created this string called S, and I've created this integer called I, and I've created them with inside the brackets of this main method. Now, this main method is actually the method that all applications use to start with. But if I wanted to, I could create another method. So let's do a static void foo. And in this one, we're going to take a string as a parameter, and we'll call it my value. And what I'd like to do is I'd like to have this method change the value of this S variable. So I might say S equals, and you'll notice that when I type in S, I don't actually get IntelliSense on that S object. The reason I don't get IntelliSense on that S object is because I defined it within this block. So its lifetime is only within this block. If I wanted to make this available outside of this block, I would have to define it at a level higher. So this curly brackets here, in this case, it's going to be the class itself. So what I can actually do is I can change this ever so slightly. And move that up to there. Where I define the value S, I assign it down here, okay, and string S, S is still, okay, define it down here, and with that defined down there, I can then start using it other places. So in this case, let me do this. You know what? Let me just make this available all the way across up there, just like that. Okay. it's defined because it's a static. So if I do static class program, well, let's not worry about that. Let's do, so what I have is I have this static method here, and I'm actually trying to assign this outside of this. We want to make this a little bit different. The idea here is that our variable that we're using is defined outside of this area. When we have it defined outside of this, we can't exactly share this data. We have to actually change our program ever so slightly. There's a couple ways we can do this. We can actually set this up inside of the console application, or I can just simply create a new project. Let me just go ahead and do this. We'll save that. And let's do a Windows format that actually creates that object for us. Let me show you what's happening here. We have our program space, and our program is the static method. However, in our form, we're not creating a static form, and I can do the exact same thing. So in this case, what I'm going to do is I'm going to add a reference to that same Visual Basic project. We'll create the same instance of the code that we had before. And actually, let me go ahead and create a new method here, private void foo. So it's going to take a string called myString, or value. We're going to have our code in here. This is actually going to say, so this.text equals hello world, something like that. And we're going to define our value. So let's make this S. So string S. So we've defined a value called string S. We're actually assigning the value here. And now this guy, foo, is actually going to reset this to whatever value we pass in here. So S equals my value. And then what I can do here is I can say this.text equals S. So this is actually just going to change the the title of the window to whatever the text I pass in. But now if I call my foo method, okay, passing in some value, in this case it takes some value, Bill was here, okay, when I run it again, I'm going to get Bill was here. Notice, however, though, that this value S is available to me everywhere, and this method was able to change it even though I set it up here. What's interesting about this is that if I move this string definition down into this box here, we're going to start to see that the compiler again gives us this error saying, hey, this S doesn't exist. This S doesn't exist because it was defined here, and once it falls out of scope, once it's done being used, it's removed from the available list of application variables that I can use. And this actually makes our lives more difficult and easier, depending on how you want to look at it. This means we can't share this. I can define memory blocks locally here, but with them defined locally here, I can't share them outside of that unless I pass them in as a value. Passing them in as a value would be something like akin to me passing in that class, the value into that class. So my class library, class 1, C equals new class library, and in this case we did a C dot get string Bill. Okay, so in this case what I've done is I've assigned the value from that Visual Basic library that I added. I passed in the Bill, and it's going to return the additional strings to that. If I comment this out, we'll see that run. Get my hands on the right keys. Insert. There we go. So now when I run this, we get the name S does not. Oh, of course it doesn't exist. We changed it. So your name is Bill, which is actually from Visual Basic. And then if I uncomment this, this method now can run, and it says Bill was here. So by doing that, we actually have the ability to alter the scope of a variable depending on where we place it. Now, interestingly enough, even though I have this value S here, I define it outside of that. I pass it into this Visual Basic class library. Once I get into here, this value that I get is actually stored in a variable called your name. What if I change the your name here to William. Okay, by assigning it your name here, rebuilding, and I'm going to re-reference this, so I'm going to refresh this guy. So it's remove and re-add that. Now when I run my code, notice that I still get Bill was here. Bill was here. Actually, let's comment this one out because it'll show you exactly how it's supposed to look. Notice that I get your name is William here. Now this is a little different than what we would expect. Even though I passed in Bill, our Visual Basic code was able to actually swap that and change and replace it with William. Now, even though this works as expected, if we go the other way, which I just did a webcast an hour ago, where we did the exact same code from Visual Basic to C#, we pass in the parameters a little bit differently. And, if you're interested in all in this concept here, in the other version, what we actually wound up doing is this value didn't change even though I overwrote it. And the reason it didn't change is because of the way the method accepted this value. In this case, it accepted it by a reference. In other words, it was pointing to the same spot in memory where it was defined. When the other way, it's actually passed by value. And instead of me passing a reference of this, it actually passes a new copy of that memory. So from Visual Basic to C#, it was passing a copy, but from C# to Visual Basic, it was actually handing a reference to it. And it allows those to switch back and forth. Now, we can actually specify in our method calls which way this works simply by specifying in our signature up here. But I'm going to get into that in a future episode. But just be aware that you might find it in some cases where a method call that you call handles the object a little bit differently than you expected it to. And if that's the case, check for whether the method is passing it by reference or by value. And that makes all the difference. So that hopefully gives you a little bit of understanding of the lifetime of an object. This object, again, can be shared, can be managed by either the local system or it can be managed by even remote systems in this case. So in this case, I overwrote the value your name, and then the value coming back from your name was actually updated even though we actually didn't expect it to be updated. So let's go ahead and save that. Go back to our slide deck. Okay, so let's wrap it up by doing a quick review of what a Visual Basic application actually looks like. Now, we did do this already. We did look at this already. However, we're going to see a little bit more advanced functionality here. We did talk about the main routine and the functions that it contains. We talked about how many, we talked about a while back how applications are actually broken up. Now, when we looked at the scope today of a variable, we noticed that the scope of the variable is the scope of the curly braces that it's defined in. So the farther out of those curly braces I go, the more visible, if you will, that code happens to be, or that variable happens to be. The value that you have in that variable happens to be as well. But also notice that we can pass that variable across from one boundary to another, depending on how the method call and the signature looks, or whether it was by reference or by value. We also saw in our code, when I added the reference to that namespace, the use of the libraries. The namespace could have been different than the name of the library. We could define it any way we want to that way. But in this case, we used a library that was built in an entirely different language than the code that we were building our application, our demo app in. So I had the library that was written in Visual Basic, but I was using it in C#. And that's actually a really important aspect of the .NET framework, the ability to take an application and use that across multiple platforms. So let's go ahead and pop back over to the program and then wrap this up by taking a look at this, the layout of this program, seeing how it differs or how it actually works as expected, and then talk about next week's episode. So in this case, we have our application. We have the exact same using statements that we had before. Now in this case, I built this new form here, and I referenced the class library directly from class library 1 namespace. I could have, if I wanted to, did the using statement and use the class library as that, and if I did that, that would eliminate the need to call these secondary namespaces, because basically I was saying, okay, I'm going to use this one, and that moves these, promotes them up to a top level so that the IntelliSense can actually see those immediately. So there you can see that class is available to me immediately. Now remember, that's a Visual Basic class, but there's nothing inside here that would let you know that that's a Visual Basic class, because the .NET Framework really doesn't care. As long as it's intermediate language-based assemblies, then the code doesn't care what it looks like from that point, from what's behind the scenes. The other thing that we did here is we have our in this case we're using a form. There is a main routine that's entering the program. However, that's over here in this program CS, and this happens to be the main entry point to the application. The main entry point to the application in this case simply creates a new instance of our form, which is this other class here, and then executes it. So this line right here actually creates a new instance of that form and executes it. And then this guy sits around and waits for this form to end. When this form exits, then it goes ahead and falls out and ends the application. So here's the new instance of our form, and this guy right here is an interesting method. Notice that his signature is a little different. He doesn't actually have a return parameter defined. The reason for that is in C#, all applications or all classes have what's called a constructor. The constructor is the method that's called when an instance of a class is created, and it's used to help set up what a class can do and what its functionality is. Maybe it needs to pre-populate some variables with certain values, for example. Well, the class constructor is actually the name of the class with simply the public keyword declared in front of it. So whenever I create a new instance of this form, this code gets executed first, and there is no return path. It just gets executed and then stops, and returns back to the normal form functioning. So you can put any type of setup code or startup code that's required inside of this constructor method, and that code will get executed. Now, this is called the constructor, but the way you call the constructor is by using the new keyword. So in this case, you'll notice that we have application.run equals, in parentheses here, we have new form 1. Anytime I want to create an instance of a class, I'm going to use the new keyword. Just like I created a new instance of the class in our class library with the new keyword, new is calling the constructor in that library. Now, Visual Basic handles constructors a little bit differently. We're not going to get into the detail in this, but just understand that it does have constructors that are identical to this, but their methods are a little bit different. They don't use the name of the class. They simply use the keyword new for their constructor. But we always call this with a new, which means, hey, make sure when you create this instance you execute this code as well. There really isn't an option for not doing that. You could eliminate any code inside there, but the constructor would always get called. Then the other thing I want to point out here is that we have, once we have our object, we actually, where we define the object defines the lifetime of that object. So again, I've defined this C object, for example, in this block of curly braces here, and that means that that C object will only exist within that curly braces. As soon as program execution leaves these curly braces, that object can be freed up by the garbage collector. The garbage collector will recognize that and say, hey, nobody else is using this C object. Let's go ahead and destroy it and free up that memory. So I didn't have to say, to shut this object down or deallocate it or do anything. Technically, you don't have to do that. If you want to, however, there are options that you can do. You can simply say C equals null, and that will basically set that value to an object of nothing, which will destroy it. Again, that's not necessary. The other thing that you can do is you can actually call dispose. There is a method called dispose on objects that allows you to destroy those objects and get rid of them as well. But we don't have to worry about that. Like I said, we can define it, and as long as it falls out of scope, the .NET Framework will recognize that and say, okay, they're no longer using this bit of code. Let's go ahead and destroy the objects that are associated with it. So hopefully that gives you a little bit of idea of how the .NET Framework works and how cross-platform compatibility works within, for example, Visual Basic and C#, but this works for really any language on the .NET Framework. They all compile down to this common language infrastructure the common intermediate language. And because they use that common ground in between, they can share their type systems, they can share their execution model, they can share the security model, and that allows for applications, even a single application to share in multiple different languages. Real beauty of this system. Next week we're going to talk about more about the variables that we just saw, the type system, and how we actually use those. We're going to look at the lifetime of those variables and how we can pass those around. We'll dig a little bit more into that by ref, by val thing. And then we're also going to take a look at a few other things. For example, we have this concept of what we call a constant. A constant is kind of like a variable. In your code, you can use it like a variable that's read-only. It's one that you cannot assign a value to, but you can use it over and over. A great example of a constant is the value pi. Pi is 3.14159265, whatever. In that case, I might not want to type in 3.14159266 whatever every single time I want to use it. Instead, I can use a pre-built version of it called pi, the value pi, pi. And wherever I want to use it, I can simply say, okay, I want to use pi as my value. Now, underneath the covers, the compiler will actually put in the real value. However, that's not relevant to our code. We can actually use this constant to take care of that. And we'll take a look at a few more other things next week as well. So until then, I say thank you. Please don't sign off just yet. We do have the evaluation coming up here. Please fill those out. Let me know how I'm doing, how we're doing, what you guys want to hear, what you want to see. And also, as always, you can contact me at my email, wsteele@microsoft.com, or follow me on Twitter at WJSteele. And until then, I'll see you. Sydney, you want to take them to the survey?
Thank you. I'd like to remind everyone that you can print a PDF of the slides by clicking on the printer icon in the lower right corner of your screen. You can either print or save those slides locally for your convenience. You should all be seeing a survey now on your slide area. If you could take a moment to fill it out before you log off, we do appreciate any feedback you leave for us. All you need to do is follow one of the 3 links provided to complete the evaluation. And with that, I'd like to extend a special thanks to Bill for today's presentation. Thank you all for joining us. You may now disconnect from the audio portion of today's conference.